Over a few posts I'll be covering vectors, maths, things like that as to do with games, how we can use them. A question came up when I was talking to a friend regarding getting one, this was specifically in 2D, getting one object to rotate to look at another object in a game environment. So what we had is we had an object looking in a particular direction and had a position, and we have another object, and we want to work out how much to rotate this object by so it is actually looking towards this second object. I'll create a simple Unity test bed shortly to show how to actually code this up, but it's worth covering the maths first, as a lot of this is trigonometry, which we'll use a lot of times within games, 3D, 2D, etc. A lot comes from a phrase which you may have heard called so car toa. So car toa. Macy mod. Part of so car toa means the sine of an angle is equal to the opposite over the hypotenuse. Let's abbreviate it to make it quick to write. Car means the cosine of the angle is equal to the adjacent over the hypotenuse. Toa is tangent of the angle equals opposite over adjacent. Oops, adjacent. These two here, sine and cosine, are used probably a lot more than the tangent. These are very useful in rotation matrices and other such things. But it does come down to what you know and the information you've got. The look at tangent is what we're going to be using. The reason for this is if we know our object A and we know our object B positions, we can calculate this line here, the hypotenuse, relatively easily. We can say the hypotenuse is equal to B minus A. That is the difference between B and A is this line, if these were done as a 2D vector. So that's to say the hypotenuse x is equal to the bx position minus the ax position, and the hypotenuse y is equal to the by position minus the ay position. So we split this up into two parts. This is just writing it as if it was a vector. We'll cover vectors in more detail shortly. So given this line, what we know is if we drop down the two lines to create the right angle triangle, hypotenuse x is this value here, hypotenuse y is this value here. It's the difference in y and the difference in x, the two components of this hypotenuse here. Now what tangent tells us is this is the angle we need to rotate our object, so we need to calculate this. This is the unknown angle. And so what we know is we know the tangent of the unknown angle is equal to opposite, so this is opposite of the angle, is the hypotenuse y, over the adjacent, which is this one here, which is hypotenuse x. So dividing hypotenuse y by the hypotenuse x will give us the tangent of the angle. We just want the angle. We just need the. Sometimes you can use the tangent of the angle to plug into matrices, etc. But if you want the actual angle, what you then need to do is do the inverse of tangent to get this. So the angle, the unknown angle, is equal to the inverse tangent of the hypotenuse y over hypotenuse x. In our case, on computers, this is usually written as atan. Again, we can do hypotenuse y divided by hypotenuse x. And this would give us the angle itself. With atan, it returns, like most maths functions in computers, it returns the value in radians rather than degrees. Now, everyone's familiar with 360 degrees in a circle. So 90 degrees 180 degrees, 270 degrees. Everyone's used to this. The computers generally work on radians. So we've got 0, at 90 we have half pi, 180 is pi, this is a 1.5 pi, and this is 2 pi. One circle in radians is 2 pi. We can convert between, if we know one, we can convert to the other. So degrees is equal to radians divided by 2 pi multiplied by 360. For convention, we cancel these down to give us radians multiplied by 180 divided by pi. Generally you do the divide after the multiply, just to save precision. And that will give you the answer in degrees. So if you have the radians, multiply 180, divide by pi, gives you the answer in degrees. Similarly, if we want no radians, quite often if you're using a cos and sine, you need the radians rather than degrees. In this case, using degrees, divide that by 360, and then multiply it by 2 pi. Again, cancelling these down slightly gives us radians equals degrees times pi divided by 180. In things like Unity, they will have a math.degree to radian and radian to degree, which is just a multiplier you use to convert between the two, as we'll see later. But this is how you do it if you ever need to. Some of you may have noticed there is one slight issue with the atan function, in where it takes the y divided by x. The problem would be if our units were, say, the x difference was 0, one unit is directly above the other, and our y difference is, say, 10. We'd plug our values in here, do 10 divided by 0. This is very bad. This will generally give you a crash. Division by 0, you can't divide by 0. You can check for this. Obviously, you could check for this before you call the function. If we're on 0, then we know that if y is directly above or below, we know what the angle will be, so we don't need to do atan. Used to be used a while ago just because doing atan is relatively slow, isn't tended to be worried about so much now. But what we can do is there's a useful function called atan2, which does the hard work for us. And this you just pass in y and x separately. It takes two variables rather than one. Again, it gives us the angle in radians. Both these go angle in radians. But the difference being this will handle the divide by 0 for us. So it will always give us the angle we need. Again, if we want the angle in degrees, we'd have to do the multiply by 180 divided by pi. So this is how you would calculate the angle between two objects. So this would give you the, if we have A and B here, calculating this angle, this is the opposite, this is the adjacent. We'll literally do the y component of B minus the y component of A. Oops, can't spell, let's start that again. A tan 2, and we do the y component of B minus the y component of A, and then we'll also pass in the x component of B minus the x component of A. And this will give us the radians of this angle here. What we'll now do is program this up in Unity and hopefully see it working. Right, so let's look at coding this up in Unity. We'll create a new project. Call it test look at 2D. We'll create a 2D package. Wait for Unity to start up. Right, so we've got our scene. What we'll do to begin with is we'll create a 2D object. We'll call this player, for instance. I haven't got any sprites loaded. I'll just use a circle and I'll scale up a little. There we go. We need to know which We need to know which direction it's pointing, so we'll create a looking, we'll create another one, another sprite, child of it, and create something that allows us to see the direction. I'll type it exactly up here. Let's move it a bit forward. Right, so there we go. So now we've got a sprite, and as you can see, as we rotate it, we'll be able to see which direction it's looking at. We generally use right for the default look at direction, as that makes life easier with the maths. What we'll now create as well is we'll create another 2D object, and we'll call this enemy. If we want anything better, we'll use this. Again, we'll scale it up. Let's position it over here. We'll change its colour. As it's an enemy, we'll make it red. Okay, so what we now want to do is use the maths that we've been looking at to make the player point at the enemy. To do this, we'll add a new script. We'll call it look at. And if we now load this up, the first thing I'm going to do is I'm going to find the game object. The one we want to look at. We'll look at a different way of doing this in a moment, but first of all, find the target object. Once we've found the target object, we need to find the position of the target. As it's 2D, it's vector 2. So this is called target pos, and it's just simply going to be the transform position. We're only interested in the 2D vector as we're working in 2D. Find our position. You could do this with a lot less lines. I'm going to split it up into multiple lines, as hopefully it'll make it a little easier to follow. Our position is literally just our transform dot position. Now we need to calculate the difference between the target and us. This is simply another 2D vector, which is equal to the target pos minus our pos. Now we have the difference. As we should, we need to use atan to calculate the degree in radians. So work out the angle in radians between the object, between us and the target. Angle in radians. It's in the math part of Unity. So we want the difference in y, difference in x. The reason why this is passed in y and then x is because that's how it was when we looked at it on paper. The first value is the opposite, which is the difference in y over the difference in x, the adjacent. We convert this to degrees. So angle in degrees is equal to, again, we could have simply done this all in the line above. As I said, Unity has a multiplier already built in, rad to deg, and as you probably saw, there's also deg to rad, depending on which way to go. Finally, set this as our rotation. So we take our transform, our rotation, and we want this to be a quaternion. We're actually going to use Euler coordinates, which are separate x, y, and z around the given axes. Because we're working 2D, we only want to rotate around the z-axis. That's the axis looking in and out of the screen. So if we use angle in degrees, right, we can save our file, which we'll then go back to Unity and run. Hopefully we'll see our sprite has turned to look at this. Look at our target. If we move our target and run it again, You'll see it's pointing at the new target. What we can do, we could add a new, just show this is working. I'll show you how to create a new, move the object to the mouse position. So move to mouse, creates a new script. Go and edit this again. The first thing we need to do here is get the mouse position. Because we're working in 2D, we need to set as a Z. I know that my camera is 10 units, or my sprites are 10 units in front of my camera. So we'll get the mouse position and give it a Z of 10. And now we'll convert to world positions, world coordinates. This just, our mouse cursor is in screen coordinates. We actually need them in world coordinates, so we can start using them in the game. So we'll use the main camera and use the screen to world point. So we pass in our screen position and it will give us back our position in the world. And so if we just simply set our position to equal that new mouse point, and that literally is the rule to that. So if we go back here, we now run our game. Hopefully, here we go. Our red object will now follow our mouse cursor. As you can see, our player always rotates to look at it. One thing I said we'd look at is, at the moment we use find object. What we could actually do is set which object we want to target. So we'll create a public variable. We don't need to find it anymore, and the target position is now going to be target.transform. We probably should have checks for if target is null, etc., but we won't worry about that in this. It's only a simple test. So if I now go back to our script, what you'll notice is we've now got a target game object. If I go to the scene and say we want to look at the enemy, then and run it, we should get the same result. There we go. So it's now following it. So hopefully that's just a very quick example of a lookat script. So we get the target position, get our position, calculate the difference between them, use atan 2 to calculate the angle in radians, and then create a Euler rotation matrix to rotate that many degrees around the z-axis, which gives us our rotation matrix. We've also actually created a move to mouse, which takes the mouse coordinates, sets the distance. I say this is a bit hard coded, but I know that's where my camera is. I find my camera is away from my sprites. Convert them to world coordinates that we can then give directly to the object. If I click on my mouse, you'll see up here our camera is 10 units behind everything, behind where the sprites are positioned, as our sprites are positioned at 0. And hence we've got the 10. It's positive 10 because they're in front of the camera, and minus 10 on the camera as the camera's moving 10 back. So hopefully that makes sense. I'll cover the camera and other bits and pieces in future posts.